All right, welcome back. So next up is now the idea of 4.4. We are graphing our log functions. So similar to the exponential function, your log function general format's got a coefficient in front, log base b, cx minus d plus a. And similar to the exponential graphs, we need to find three concepts: domain and range, now a vertical asymptote rather than a horizontal asymptote, which when you think about makes sense. Logs and exponentials are inverses. So the exponential had a horizontal, we do the switching of x and y, so it makes sense log has a vertical asymptote. And we still have three special points to consider. So your domain and range, so the domain now will vary depending upon whether or not the coefficient of c is positive or negative. Not about a. A will do its own thing, but it's all about c being positive or negative for which direction we're going. If c is positive, we're going to go from the vertical asymptote to infinity. Whereas if c is negative, we're going to go from negative infinity to the vertical asymptotes. Unlike the horizontal, vertical asymptote, it's not the e, it's also not the d value. We're going to see what it is in the next slide there. Range will be all real numbers, so negative infinity to infinity. The vertical asymptote will be found by solving the equation cx minus d equals 0. Because when we talked about those properties of logs, we can't evaluate logs at 0 or negative numbers. So we need to know when would we have the log be at 0, and that's where the cutoff point is, and the graph will either be all to the left of that or all to the right of that based on what's going on with C. So our three special points we're going to work with now, similar to the exponentials, only rather than being negative 1, 0, and 1, it's 1 over b, 1, and b itself. They have to correspond to the base. So if we're trying to graph this one right here, we are recognizing that the vertical asymptote, we're going to do that first. So x minus 2 equals 0, x equals 2, so our vertical asymptote is x equals 2. Which means our domain is, since c is positive, vertical asymptote to infinity. Your range will always be negative infinity to infinity. As for your three special points, we're going to do x minus 2 equals 1/4, x minus 2 equals 1, and x minus 2 equals 4. 1 over the base, 1, and the base itself. And the reason for that. So the reason for that is very straightforward. So we have, we're going to have 2.25, 3, and 6. And the reason for that is, so if I were to go through and evaluate what happens when I substitute in the 2.25, so I would log base 4 of 2.25 minus 2 plus 1. That becomes log base 4 of 1/4, really, because 0.25 is what's left over. When we have log base of the reciprocal of the base, that result is negative 1. And negative 1 minus 2 is negative 3. And then we substitute the 3 in. 3 minus 2 is 1. Log of 1, no matter what the base is 0. So 0 minus 2, I don't know why there's a minus 2, that should be plus 1. So that was a 0, sorry. So anyway, so it's plus 1, so log of 1 is 0, 0 plus 1 is 1, and then plugging in 6, 6 minus 2 is 4, log base 4 of 4 is just 1, 1 plus 1 is 2. So what's actually kind of nice about the log problem is, once you find that first one, the y values are going to be going up or down based on the value of a, the coefficient in front of the whole thing. So as you can see, we're not multiplying by anything. We're multiplying by 1 then, so the y values are going up by 1s. So it's kind of a neat little trick you can use. So we plot our vertical asymptote. We plot our points 2.250, 3, 1, 6, 2. You're going to see your curve goes along the vertical asymptote and then kind of goes flat. So each of the shapes are either going to go up like that, or it's going to come down to go flat, or it's going to go up and then left to go flat, or down to then go left to go flat. So that's going to happen based on whether or not c is positive or negative, and whether or not the value of a in front, or the base log is either an integer or a fraction. So like here we can see that our vertical asymptote, negative x minus 1 equals 0. We get negative 1 for our vertical asymptote. And because c is negative, the domain is going to go from negative infinity to negative 1. So we're going to see everything is going to exist to the left of the vertical asymptote this time. Our range is always negative infinity to infinity. So we would set negative x minus 1 equal to 1/2, negative x minus 1 equal to 1, and negative x minus 1 equal to 2. Solving those out, we are going to get a negative 1.5, a negative 2, and a negative 3 for our x values. Substituting negative 1.5, we get log base 2 of positive 1.5 minus 1, which is a half. Log base 2 of a half is negative 1, minus 3 is negative 4. We substitute negative 2. Negative of negative 2 is 2, minus 1 is 1. Log base 2 of 1 is 0. 0 minus 3 is negative 3. And again, we're noticing we're going up by that value of a in front. So this next one would be negative 2. So we go ahead and plot all our information. Vertical asymptote at negative 1. X, negative 1.5, negative 4. Negative 2, negative 3. Negative 3, negative 2. So our graph's going to look kind of like this. Again, flat on the left and going vertical on that along the vertical asymptote. So in both those cases, our base was an integer. Let's explore now when the base is a fraction. So vertical asymptote still x minus 3 equals 0, still occurs at 3. So there's our vertical asymptotes. C is still positive, so the domain would still go from the vertical asymptote to infinity, whereas range still goes from negative infinity to infinity. As for our 3 special points, it's still x minus 3 equal to the reciprocal of the base, so it would be 4, equal to 1, and equal to the base itself. So we'd get 7, 4, and 3.25. Substituting in 7, 7 minus 3 is 4. And again, remember, we're doing log 1/4 of 4. When the base and the number are reciprocals, the result is always negative 1. So it's negative 1 plus 2, which is 1. Log base 1/4, 4 minus 3 is 1. So log of 1 is always going to be 0. 0 plus 2 is 2. So again, you see we're increasing by a, so this last value is going to be a 3. But you would check that. You'd have 3.25 minus 3 is a quarter. Log base a quarter of a quarter would just be 1. 1 plus 2 is 3. So we go ahead and plot our information, vertical asymptote occurring at 3. Points at 7, 1, 4, 2, and 3.253. So you can see it's coming from above and then going flat from there. So it's always going to come from above when we're dealing with a fraction base. We're also assuming each one of these problems, we're going to do, because a is not really affecting it too much. It's just going to be a positive 1 value there. If a was negative, it actually then flips it, because then it requires us to reflect over the x-axis, so it'll come from below. So rather than dealing with that kind of insanity, we're just going to deal with just always a being 1, so it's a consistent kind of format for those graphs. All right, one more. Let's talk about now we have a negative coefficient there for the x and the fraction base. So we still find the vertical asymptote setting equal to 0. Getting a negative 2 for the vertical asymptote. The domain, because c is negative, goes from negative infinity to negative 2, so it's the left side of the graph. Range is everything, negative infinity to infinity. 3 points, it's negative x minus 2 equals 2, the reciprocal of the base. Negative x minus 2 equal to 1, and negative x minus 2 equal to 1/2 the base itself. So we would get negative 4, negative 3, and negative 2.5. Substituting in the negative 4, negative of negative 4 is 4. 4 minus 2 is 2. Log base 1/2 of 2 would be negative 1, plus 3 is 2. And then we're recognizing, as we've been seeing for all the other examples, the y value is going to increase by 1 here. So that should be a 3, which makes sense. Negative of negative 3 is 3, minus 2 is 1. Log base 1/2 of 1 is 0. 0 plus 3 is 3. And then this should be a 4. If you plug in the negative 2.5, that would make sense for that particular portion of it. So we plot our information. Vertical asymptote at negative 2, negative 4, 2, negative 3, 3, negative 2.54. So it's coming from above. So we go vertical from above, hit our points, and start going flat. And there's our log graphs. You will find the shapes are very similar to the exponentials. In fact, if you were to kind of take this thing and kind of like twist your head a little bit, you would see it looks the exact same idea as like going flat along the horizontal and then going up. So it's still keeping the same kind of idea there. All right, so that's all our properties of exponential logs. That's our graphs of the exponential logs. So the next couple of years, the next series of videos will be based on the solving of the exponential log equations. So I'll see you next time for those videos.